The inverse tangent function, \tan minus $1. Welcome, everyone. In this subsection, we are going to explore the inverse of the tangent function. Now, before we dive directly into the inverse, it is essential that we first analyze the behavior of the original tangent function. We need to do this because, as we will see in the upcoming slides, we cannot simply invert the function in its entirety. We must first understand why a specific restriction on the domain is necessary to properly define its inverse. Analysis of the tangent function, \tan x $. Now that we have introduced the concept of the inverse tangent function, let us begin by reviewing the properties of the standard tangent function, f of x equals tangent of x, as this foundation is essential before we can define its inverse. First, let's examine the domain. The tangent function is defined for all real numbers, except for those specific values where the cosine of x equals 0. In mathematical terms, the domain is the set of all real numbers excluding odd multiples of pi/2, where n represents any integer. Next, we look at the range. The tangent function can take on any real value, extending from -infinity to +infinity. Therefore, its range is simply the set of all real numbers. Now, we must address a critical conceptual hurdle, the problem of bijectivity. For a function to possess an inverse, it must be bijective, which means it must be both one-to-one and onto. However, the tangent function is periodic with a period of pi. This implies that the function repeats its output values every pi units. For instance, the tangent of 0 is 0, and the tangent of pi is also 0. Because multiple different inputs produce the exact same output, the function fails the one-to-one requirement. Consequently, an inverse cannot exist for the function across its entire domain. This creates a problem that we must solve, which leads us to our next topic, restricting the domain to create a bijective branch. Restricting the domain. Now that we have established why the tangent function is not naturally one-to-one over its entire domain, let us look at how we can resolve this issue. To make the tangent function one-one, we must restrict its domain to a single branch. We choose a section of the graph where the function is strictly increasing and still covers all possible values of its range. The standard restriction used in mathematics is the open interval from -pi/2 to pi/2. To be precise, our restricted domain is now the interval between -pi/2 and pi/2, while the range remains all real numbers. By limiting ourselves to this specific interval, every value in the range is mapped to exactly one unique value in the domain. This transformation makes the function bijective, which is the essential condition we need to formally define the inverse tangent function, which we will cover in the next slide. Defining the inverse tangent function, \tan minus $1. Now that we have established the need to restrict the domain to make the tangent function bijective, let us formally define the inverse tangent function. If we have the function y equals tangent of x, where x is restricted to the open interval from -pi/2 to pi/2, then the inverse function is defined as x equals inverse tangent of y. You will also frequently see this written as arctan of y. Both notations refer to the same inverse operation. Let us now examine the key properties of the inverse tangent of x. First, regarding the domain. As a general rule for inverse functions, the domain of the inverse is the range of the original function. Since the range of the tangent function is all real numbers, the domain of inverse tangent of x is the set of all real numbers. Second, let us look at the range. The range of the inverse function is the restricted domain of the original function. Therefore, the range of inverse tangent of x is the open interval from -pi/2 to pi/2. It is very important to remember that this specific range, from -pi/2 to pi/2, is known as the principal value branch. This concept is crucial, as it ensures we get a single, unique output for every input, which we will apply in the upcoming practical examples and calculations. Real-world application, finding the angle of elevation. Now that we have established the theoretical definition and the restricted range of the inverse tangent function, let us look at how this is actually applied in the real world. In fields like trigonometry and physics, the inverse tangent function is essential when we need to find an unknown angle, provided we already know the lengths of the opposite and adjacent sides of a right-angled triangle. To illustrate this, let us consider a practical example. Imagine a surveyor standing 10 meters away from the base of a building, and the building itself is 10 meters tall. Our goal here is to find the angle of elevation, which we will call theta, from the ground up to the top of the building. We begin with step 1, identifying the trigonometric ratio. As we know, the tangent of an angle is the ratio of the opposite side to the adjacent side. In this case, both the height of the building and the distance from the base are 10 meters. So, the tangent of theta equals 10 divided by 10, which simplifies to 1. Now we move to step 2. To isolate the angle theta, we must undo the tangent operation. This is exactly why we need the inverse tangent function we discussed in the previous slides. By applying it to both sides, we find that theta equals the inverse tangent of 1. Finally, in step 3, we determine the principal value. We need to find an angle whose tangent is 1. We know from our standard values that the tangent of pi over 4 equals 1. Since pi over 4 falls within the principal value branch, which, as a reminder, is the open interval from negative pi over 2 to pi over 2, this is our correct value. Therefore, the angle of elevation theta is pi over 4 radians, which is equivalent to 45 degrees. Step-by-step calculation of principal value. Now that we have seen a practical application of the inverse tangent function, let us walk through a formal, step-by-step calculation to find a principal value. We will use the expression inverse tangent of negative square root of 3 as our example. First, in step 1, we begin by setting the entire expression equal to a variable. Let's call it y. So we write y equals inverse tangent of negative square root of 3. This simply gives us a target value to solve for. Moving to step 2, we need to rewrite this in terms of the original tangent function to make it easier to handle. By the definition of inverse functions we discussed earlier, we can rewrite this as tangent of y equals negative square root of 3. Now, in step 3, we must identify the angle y that satisfies this equation. We recall from our standard trigonometric values that tangent of pi over 3 equals square root of 3. However, since our current value is negative, we need to find an angle that results in a negative value while remaining within our restricted domain. Because the tangent function is odd, we know that tangent of negative pi over 3 equals negative tangent of pi over 3, which gives us the negative square root of 3 we are looking for. In step 4, it is crucial to verify if this angle actually falls within the principal value branch. As we established in the previous slides, the range of the inverse tangent function is the open interval from negative pi over 2 to pi over 2. Since negative pi over 3 falls comfortably within this interval, it is a valid principal value. Therefore, our final answer is the principal value of inverse tangent of negative square root of 3 is negative pi over 3. Keep this process in mind, as we will summarize these key takeaways in the next slide and discuss some common pitfalls to avoid. Key takeaways. Now that we have walked through the theoretical foundations and a practical calculation, let us summarize the key takeaways from this section to ensure everything is clear. First, recall our earlier discussion on bijectivity. The original tangent of x function is not one-to-one because it is periodic, meaning it repeats its values. Therefore, we must restrict its domain to the open interval from negative pi over 2 to pi over 2 to make it bijective, which is a necessary condition for an inverse to exist. Next, let's look at the properties of the inverse function. The domain of the inverse tangent of x is the set of all real numbers. This means that regardless of the value you provide as an input, the inverse tangent function will be defined. However, the range, which we refer to as the principal value branch, is limited to the open interval from -π/2 to π/2. It is important to remember that the output will always fall within this specific window. In simple terms, the inverse tangent function is a tool that returns the specific angle whose tangent is equal to x, provided that the resulting angle stays within that principal value branch we just mentioned. Now, while these points seem straightforward, there are a few conceptual traps that students often fall into. Let us move to the final slide to discuss these common mistakes so you can avoid them in your exams. Common mistakes. Now that we have covered the theory and practical calculations, let us conclude with a very important slide on common mistakes. It is quite easy to fall into these traps, so please pay close attention. First, let's discuss confusing notation. A very common error students make is treating tan inverse x as the reciprocal of tangent x. It is crucial to understand that tan inverse x refers to the inverse function, which gives us the angle. On the other hand, the reciprocal of tangent x, written as tangent x to the power of -1, is equal to 1 divided by tangent x, which is the cotangent of x. Please remember that these two are entirely different mathematical concepts. Secondly, let's look at the use of brackets. When writing the range of the inverse tangent function, students often mistakenly use square brackets instead of parentheses. As we discussed in our analysis of the tangent function, tangent is undefined at plus or minus π/2 because of the vertical asymptotes. Therefore, the range of tan inverse x must be expressed as an open interval from -π/2 to π/2. Using square brackets would imply that the endpoints are included, which is mathematically incorrect in this case. Finally, be careful not to ignore the principal branch. If you are solving the equation tangent of y equals 1, you will find that there are infinite solutions, such as π/4, 5π/4, or -3π/4. However, when you are asked specifically for the principal value of tan inverse of 1, only π/4 is the correct answer. This is because, as we established in our earlier slides, the principal value must lie strictly within the interval from -π/2 to π/2.